welcome back for Chapter 5, the standard deviation as a ruler and the normal model. What I'd like you to do is consider the stem plot to the right, which displays for the 200-meter race and long jump in the 2016 Olympic heptathlon. Katarina Johnson-Thompson are the scores in green, and she won the 200-meter, and Nafisatu Tiem are in the red scores, and she won the long jump. So which of the two winning scores is the better one? If we take a look, it's kind of hard to compare a run and then a long jump. So a run is calculated in seconds, so time, and then a long jump is calculated in meters, which is distance. So how do you compare time versus distance or seconds versus meters? What we need to do is we need to standardize in order to place those values on the same scale, so to speak. Expressing a distance from the mean in standard deviations standardizes the performances. Okay, you may have heard of like standardized test scores. So SAT is considered a standardized test. You know, your scores is being compared to others who took the same test. To standardize, what we do is we subtract the mean, and then we divide this difference by the standard deviation, which we're familiar with at this point. If you want to look at a formula for that in words, it's just to find what we call z, which is your standardized value. We do the value minus the mean and then divide by the standard deviation. And in symbols, it's just y minus y bar. Remember, y bar is your sample mean. And then we divide by the standard deviation, S, which is your sample standard deviation. And these are called standardized values. And they're commonly denoted with the letter Z. Okay, usually we just call them Z-scores. And we're going to be finding those and seeing those a lot. And all they do is they just measure the distance of a value from the mean in standard deviation units. Okay, here's an example. Please pause the video, give yourself time to read the problem, one time or a few times, and then unpause when you're ready to work it out together. The men's super combined skiing events consist of two races, downhill and a slalom. 37 skiers finished both races. Times for the two events are added together, and the skier with the lowest total time wins. There is ongoing debate whether this format favors technical slalom skiers or the downhill specialists. At the 2018 Winter Olympics, the mean slalom time was 50.13 seconds with a standard deviation of 3.58 seconds. The mean downhill time was 81.72 seconds with a standard deviation of 1.4 seconds. Marcel Hirscher of Austria, who won the gold medal with a combined time of 126.52 seconds, skied the slalom in 45.96 seconds and the downhill in 80.56 seconds. On which race did he do better compared to the competition? So before we solve this, we want to make sure we understand what we're looking for. We're trying to compare two different events or two different races, and they give us information about both. So they tell us that the mean downhill time was 81.72 seconds with the standard deviation of 1.46 seconds. And we also know that the mean slalom time was 50.13 seconds with the standard deviation of 3.58 seconds. And I know that Marcel won the gold medal with a combined time of 126.52 seconds, and that's for the combined time, and then skied the slalom in 45.96 seconds and the downhill in 80.56 seconds. Okay, so we want to know which race did he do better compared to the competition. So in order to do that, since I have two different races, I need to standardize them, and I'm going to convert them to z-scores. So the first thing I'm going to find is z, and then a little subscript to kind of separate the two. We're going to have to find z slalom and then z downhill. So you can just call it like zs and zd if you wanted to show the difference. So how do I find a z-score? Remember, it's the value minus the mean divided by the standard deviation. So the value I have for slalom is 45.96, and I'm going to subtract the average time for the slalom, which was 50.13. And then I'm going to divide by the standard deviation for the slalom, which is 3.58. And when I do that, I get negative 1.16. Okay, so if you're not sure how I got that, you can subtract these two and then take your answer and divide by 3.1.58. I'm going to do the same thing for the downhill, except this time the value, Marcel's value was 80.56, and I'm going to subtract the average for the downhill, which was 81.72, and then subtract the standard deviation for the downhill, 1.46. And when you do that, you get negative 0.79. Okay, so which of those scores would be better when you're thinking in terms of time, right, in seconds? And we definitely want to be more under time, right? A positive z-score in this case would mean it took longer. So negative is a good thing. It means that he's fast. And here we can see that negative 1.16, if you're looking at the number line, right, would be a lot lower than negative 0.79. So the slalom is the better time. So Marcel's slalom time was better than the downhill time. Okay, so take a second, pause the video, and you can read through this and then try these problems on your own. Your statistics instructor has announced that the lower of your test scores will be dropped. You got a 90 on test 1 and an 80 on test 2. You're all set to drop the 80 until your instructor announces that she grades on a curve. She standardized the scores in order to decide which is the lower one. The mean on the first test was 88 with a standard deviation of 4, and the mean on the second was 75 with a standard deviation of 5. Which test will be dropped, and does this seem fair? Explain. Okay, so we've got two tests, right? Again, so we're looking for which test will be dropped. Okay, so what do I know? That you got an 80 on test 1 and a 90 on test 1 and an 80 on test 2. And we also know that the mean on the first test was an 88 with a standard deviation of 4, and the mean on the second was a 75 with a standard deviation of 5. So I need to find a z-score. Okay, so we got z-score for test 1, and we need the value. So you got a 90 on test 1, and the mean on test 1 was an 88 with a standard deviation of 4. So here I've got 2/4, which reduces to, or changes to 0.5 as a decimal. And then we're going to do the same thing for test 2. And on test 2, you scored an 80. The mean was a 75, and the standard deviation was a 5. So 5 divided by 5 is 1. Okay. So what does that mean? Well, this is the number of standard deviations above the mean, since it's positive. On test 1, you scored a half a standard deviation above the mean. On test 2, you scored 1 standard deviation above the mean. So which test would be dropped? The test that would be dropped would be test 1 because it has the lower z-score. Okay, does this seem fair? What do you think? Since the second test is 1 standard deviation above the mean, which means it's farther away from the first test, it's a better score relative to the class. So yes, this would be fair. So yes, the second test is 1 standard deviation above the mean, or away from the mean, however you want to write it. Further away from the first test. So it's a better score relative to the class. And that is the end of this part 1 video. Please come back to talk about what happens when we take data and add and subtract, and then divide, how that affects the mean and the other measures of center and the measures of spread.